today we'll discuss probably the most important application of the method of the solution of linear differential equations with linear coefficients, namely the harmonic oscillator. So let's start. So here is our Schrödinger equation. So here psi is our wave function, and this is our potential well. Everyone obviously recognizes the potential well of their harmonic oscillator, a simple parabola. Okay, and for brevity, we'll set h bar equals to 0 in everything what is to follow. Right. So the first thing we notice about this equation is that it has quadratic coefficient here, our potential. So our bet actually is to get rid of it, because there is no general procedure to solve differential equations with their quadratic coefficients. So how can we get rid of this quadratic term? Well, the best thing we could do is actually to find the asymptotic behavior of our solution at large values of x. Why? Because at large values of x, there is a hope that the solution somehow simplifies and the equation simplifies. Right? But before we do so, let's actually introduce some suitable rescaling of our differential equations to make things simpler. Okay, so here it is. So first we rewrite it. We multiply it by 2m. And we tune our rescaling parameters. So x, suppose, is equal to some coefficient beta times y. Right. Then psi prime prime xx is turned into psi prime prime yy divided by beta squared. Now our equation becomes, okay, let's write it down here. It's minus psi prime prime divided by beta squared plus m squared omega squared beta squared y prime y squared psi equals to 2m e psi. So E is our energy, obviously. Sorry, I forgot to mention it. And m is the mass of our particle. Right, so let's multiply both parts by beta squared. Now we get and let's choose this beta parameter in such a way that this coefficient becomes 1. So beta squared is equal to 1 over m omega. And then the equation is turned into a simpler one. So it's just minus psi prime prime plus y squared psi equals to 2e divided by omega times psi. Right. So and now let's put this double derivative term into our right hand side, and we get psi prime prime minus y squared plus minus 2e divided by omega psi equals 0. Okay, so again, so the equation is looks more elegant, definitely, but we can't solve it. So let's study its behavior at large values of y. So when y is large, one can dispose of this second term because we consider that y is much greater than the square root of e over omega. Then our equation becomes psi prime prime minus y squared psi equals 0. But the problem, even this equation can't be solved exactly. So again, we will try to solve it with some suitable change of variables. And we will definitely use the fact that y is large. So our next suitable choice is so-called semi-classical choice, semi-classical change of variables. So we introduce the new function as follows. Psi equal to e to f. And then we rewrite our differential equation in terms of this new action-like variable f. So psi prime now becomes f prime times e to f, and psi prime prime becomes f prime prime plus f prime squared times e to f. And let's plug this into our simplified asymptotic equation. So now we get f prime prime plus f prime squared equals to y squared. So yeah, probably it does look a little bit simpler, but now it's non-linear because it has this f prime term squared. But let's hope that we can solve it somehow, at least at large values of y. So again, it can't be solved exactly. So let's make some initial assumptions about the structure of our solution, and then we'll check if it's correct a posteriori. Our first bet is the assumption that probably at large values of y, f prime prime, the second derivative, is much greater than the square of the first derivative. So one can actually discard the second term in our left-hand side. Then the equation becomes almost trivial. F prime prime equals y squared. And we can elementary integrate it at least once. F prime now becomes y cubed over 3. Well, actually plus some constant, but since y is large, we can discard all the constants altogether. So again, now we can actually check if this initial assumption holds. So f prime prime is y squared, and it should be much greater than f prime squared. So, but f prime squared is y to 6 divided by 9. So for large y, it's obviously wrong. So this assumption is actually wrong. And let's try another one. And another one is f prime squared is actually much greater than f prime prime. Let's see if this works. So now we can discard the first term in our differential equation. As a result, we get f prime squared equals y squared, and f prime equals plus minus y. Again, let's integrate this thing. Actually, before we integrate, let's check if our condition holds. So f prime equals y. So the modulus of f prime is simply modulus of y. And f prime prime is the modulus of f prime prime is 1. So, and indeed, f prime squared is modulus y squared is much greater than 1. So it does hold. And the result, we find the asymptotic solution for this simplified differential equation. So f prime equals to plus minus y, and f equals to plus minus y squared over 2. And our asymptotic solution becomes psi equals e to plus minus y squared over 2. All right. So which of these asymptotic solutions to choose? And actually, why were we so interested in this? Well, the idea now is to seek the exact solution of our differential equation. Where is it? It's here. This is our exact differential equation. So the idea is to seek it in the form of in the special form, so-called ansatz. And we introduce this asymptotic function and some new function, let's call it phi. And then we recast our initial differential equations in terms of this new function phi. And the question is, shall we choose plus or minus sign here? Well, both choices are okay. But the simplest choice, which leads us straight to their solution, is minus sign. And it's kind of more natural because we expect that our particle, when it oscillates, it is it's centered near the origin, oh, here is our x origin or y origin, right? So because if we choose, for example, plus sign e2 y squared over 2, then as you remember, the modulus squared of psi function gives us the probability to find particle, its particular coordinate y. And then, so if we choose plus, the tendency that the probability can actually grow as y grows, which is counterintuitive. So let's choose minus sign first, and then write down the solution. Later on, I'll discuss the case when we choose plus sign. And then the solution is a little bit more complicated, but still, it's doable. Okay.